Welcome to All This Math. This is Professor Parker, and today we're doing some work with the so-called Pythagorean Theorem. Now, you might ask, why do I say so-called Pythagorean Theorem? I say so-called because the person known as Pythagoras in history actually studied in ancient Kemet, which is now modern-day Egypt, but he studied in ancient Kemet for about 22 years, where one of the mathematical formulas that he was introduced to was what is now known as the Pythagorean theorem. So, and this is information that can be gathered when we study scholars, African scholars like Theophile Obenga, who studied under the late Sheikh Anta Diop or Sheikh Anta Diop. And we find out this information. And we find that mathematics is actually in our cultural DNA. So don't let people let you think that, black people shouldn't be doing math, because we've been doing math for thousands and thousands of years. But moving right along, we have two right triangles, right? And when we want to figure out missing sides in right triangles, we use, as I said, so-called Pythagorean theorem. All right. Now, we use this theorem or this formula. We use this formula, I should say, because there's a theory, right, that leads us to a formula, right? And we can use this formula when we're dealing with right triangles. Now, how do I know that these are right triangles? I know because of these boxes in the corners. So this means that this is a 90-degree angle, thus making this a right triangle. This has a box in the corner, thus making this a right triangle. So I know I can use the theory or the formula a squared plus b squared equals c squared. That is the Pythagorean theorem. So we write that down, right? A squared plus b squared equals c squared. All right? That's where we start. Okay. Now, we look at the triangle and we look at the information that we know, and then we look at the information that we don't know but need to figure out. So here I have a 19, a 17, and an x. All right. Now, what are those? This 19 is something called the hypotenuse. You want to put that in your notes. Hypotenuse. Write that up here. Hypotenuse. That's called the hypotenuse. Now, when you look at a triangle, this is how you know which side is the hypotenuse. You look for the right angle. In this case, the right angle is right here. The hypotenuse is always directly across from the right angle. Hypotenuse is over here. All right? Across from the right angle. Here's the right angle. Hypotenuse is across from it. Right here, this side. And the hypotenuse is always going to be the longest side in a right triangle. Right? It's going to be longer than the other two legs. So when you think of a right triangle, keep in mind that you have two legs and a hypotenuse. Two legs and a hypotenuse. Two legs and a hypotenuse. Like two pieces in a biscuit, right? If you eat chicken, right? That's a way to think about it, a way to memorize it, right? Two legs and a hypotenuse. All right? Two legs and a biscuit. That's how I memorize it. We'll keep it in mind. All right? Now, then we go to the formula and we say, okay, well, how am I going to use this formula? How is this formula going to help me? The formula helps you because you can take information about this right triangle and plug it into this formula by replacing some of these letters. Now, A and B are always the legs. A and B are always the legs. C is always the hypotenuse. A and B are the legs. C is the hypotenuse. Now, how do I use this information? If I look at this triangle and I say, okay, my two legs are 17 and x. X is what we're trying to figure out. So I'm going to replace A with 17. And now instead of A squared, I'm going to have 17 squared. And then I write a plus sign. And I'm going to replace the B. I don't actually have to replace the B, but I'm going to just to be consistent, since the length of the side is labeled as x. So I'm going to replace the B with an x. So I got x squared. And then I write my equal sign. And then, like I told you, C is always the hypotenuse. And where is the hypotenuse? Across from the right angle. And how long is the hypotenuse? 19. So I'm going to replace the C with a 19. So I put the 19 right here with the exponent 2. So this is how I use the Pythagorean theorem, right? This is how I use it, right? I replace A with 17. I replace B with X. I replace C with 19. Now, somebody might wonder, and this is an excellent question. You might be sitting at home thinking about this right now. Like, does A got to be 17? Could A be X? And could I switch them? And could B be 17? You're absolutely right. You can. And that's a good question if you had that question. When you're dealing with the legs, just know that A and B have to be the legs. But there's no particular leg that has to be A. There's no particular leg that has to be B. It doesn't matter. You will end up with the same exact answer. If I wrote this as x squared plus 17 squared equals 19 squared, at the end of the day, we're going to get the same answer for x. We're going to get the same exact answer for x at the end of the day. All right? Now, let's get to the math. Now, because I had a teacher in 7th grade that had us memorize all the perfect squares from 1 squared up to 25 squared, I could do this without a calculator. And I suggest you do that too. That's why I brought up that little story about what I had to do when I was in 7th grade. I actually wish I had done it before 7th grade. I recommend that you memorize all the perfect squares. So when you see a problem like this, you don't even got to go to your calculator and say, oh, what's 17 times 17? Or what's 17 squared? You don't even got to worry about all that. Memorize your perfect squares from 1 squared up to 25 squared at a minimum. Keep going. You can go past 25. You can memorize all the perfect squares up to 50 squared, right? You know, to your heart's delight. You can keep on going. You know, there's no limit, right? But at a minimum, no 1 squared through 25 squared. So 17 squared is 289. So this gets replaced with a 289. Right? Now, also keep in mind that that exponent means that you multiply 17 times itself. Right? It does not mean that you do 17 times 2. Because 17 times 2 will be 34, and that will be wrong. You don't want to do that. We need to know how to use exponents properly. All right? So now, we can't do anything with the x, because that's an x. We can't do nothing with that. That's just x squared. Then you write your equal sign, and then you got 19 squared. Again, this does not mean 19 times 2. That's not what that means. That means 19 times 19. What an exponent tells you is, if you were to rewrite this as a multiplication statement, how many times would this number show up? How many times would this 19 show up? So if I rewrite this as a multiplication statement or a multiplication problem, 19 would be shown or be written twice. 19 times 19. That's 2 19s because the exponent is a 2. 19 squared. I also memorized that one back in the day. 19 squared is 361. Boom. Now, my goal, since this is an equation, right? My goal is first to isolate x squared. I want to get x squared all by itself, right? So that means on the left side of the equal sign, I want x squared all by itself. So that means I have to get rid of 289. Now, how do I get rid of 289? Well, 289 is a positive number. When we want to get rid of things within equations, we do opposite operations. The opposite of a positive 289 is a negative 289. So that means I'm going to subtract 289 from 289, and then I slide over to the right side of the equation under the 361. I subtract 289 over here. Also, boom, that's gone. I bring the x squared straight down. I bring the equal sign down. Now I got to do a little bit of arithmetic. 361 minus 289 to get down to 300, that's 61. To get from 89 up to 300 is 11. So really I'm doing 61 plus 11. 61 plus 10 is 71. And then to add the extra 1, that's 72. That's how you want to do the mental math. Right? So now I got x squared isolated. Now in order to solve for x, I got to get rid of this exponent. I got to get rid of the exponent because I don't really care what x squared is. This is just a means to an end. This is how this is just working through the process. But I want to know what x is, right? Notice this does not say x squared. So you don't stop right there. You're not finished yet. We want to know what x is. So we got to get rid of the exponent. The way you get rid of an exponent too is by taking the square root. Put that down in your notes. Remember that. The way you get rid of an exponent is by taking the square root. Or if you were trying to get rid of an exponent 3, you would take the cubed root. If you were trying to get rid of an exponent 4, you would take the 4th root, and so on and so forth. So then I'm going to do this. Square root of x squared is equal to the square root of 72. All right. Now, if this was like pure algebra, I would put a plus or minus sign here because technically the square root of 72 has two answers, a positive value and a negative value. But since we're dealing with geometry and there's no way that the length of this the side of this triangle can be a negative value, I'm not concerned with the negative value. But that's just a little sidebar, right? That might not even be relevant right now to some of us. All right, but anyway, I take the square root of x squared, which gives me x. Now, 72, my first question is that a perfect square? Meaning, is there a whole number that can be multiplied by itself or squared that will equal 72? There is not. Because 72 is in between two perfect squares. 72 is less than 81. 81 is a perfect square because 9 times 9 is 81. And 72 is greater than 64, which is another perfect square because 8 times 8 is 64. There's no whole number in between 8 and 9. It doesn't exist. At least not in our number, not in our real number system. All right. So therefore, 72 is not a perfect square. So I'm going to show you how to show the answer in two different ways. The first way, we're going to simplify this radical. This is called a radical because it's the square root of 72. It has a radical sign around it, right? So when you encounter a situation where you have a number under the radical sign, which is also known as a radicand, I'm big on vocabulary. Right? This 72 is called a radicand, right? You want to think about what perfect square do I know that is a factor of that radicand? And not only that, you want to think about the biggest one, because sometimes these radicands be having, multiple perfect square factors. But if you don't pick the biggest one, then you're going to have to keep doing the step over and over again, right? So you want to always pick the biggest perfect square. Case in point, with 72, the biggest perfect square factor of 72 is 36. 6 times 6 is 36, right? So you want to break 72 down into 36 times 2. That's what you want to do, right? So it's going to look like this on your paper, 36 times 2. Now, the purpose of doing that is so I could pull this 36 out, because 36 is a perfect square. Because 36 is equal to 6 times 6. So 36 is a perfect square. So the 36 can come out of the radical sign. But when it comes out, it's not a 36 no more. It's a 6, because 6 times 6 is 36. So now, why do I have two equal signs written? What is going on? All right, so now I got x equals, now the 36 came out and turned into a 6. The 2 can't come out. The 2 can't come outside. The 2 got to stay in the house because 2 is not perfect. But the 2 will be all right, though. So we write the 6, and we got the square root of 2. Now, what would have happened if I didn't use 36? Because 72 has other perfect square factors, such as 4, right? 4 times 18. 4 times 18 is 72, and 4 is a perfect square, right? So don't always use the first perfect square you think of, because if you'd have did that, watch what would have happened. You'd have had 4 times 18. The 4 comes out, turns into a 2, and you'd have had 2 times the root of 18. But that's not simplified all the way, because then 18 could be broken down. Because you could break 18 down into 9 times 2. And then the 9 will come out and turn into a 3. So now you got 2 times that 3 times the root of 2. But look, what's 2 times 3 anyway? 2 times 3 is just 6, root 2. So you see all the trouble you would have saved yourself and the time you would have saved yourself? All you got to do is just take the biggest. You want to take the biggest perfect square factor. You don't want to play around. Don't play around with the small perfect square factors. Now, if you got a real huge number and you don't really know how to maneuver with it, then you might have to go step by step. There's nothing wrong with that. But with a number like 72, you want to think about what's the biggest perfect square that's a factor of 72? And you want to pull that out, right? You want to first break the number down into those two numbers. And then you want to take the square root of that perfect square. You want to do it like that. So for this one, our final answer in radical form is 6 root 2, right? But what if your teacher doesn't want you to write it in radical form? What if they want you to round it to the nearest decimal place or to the nearest 10th place or whatever, right? Then what you would do is say, okay, well, if x squared equals 72, I take the square root of 72. In terms of your calculator, and I did this already, I don't know this off the top of my head, but the square root of 72 is also 8.49. So that's in decimal form, right? That's decimal form, 8.49. Okay? So this is two ways to show what x is equal to. X is equal to 6 root 2. X is also equal to 8.49. Now, this example I wanted to do because this is an example of a right triangle that's missing a leg, right? But then you have right triangles that are missing the hypotenuse, right? So we use the same formula, but we just do the problem a little differently. And actually, when you're missing a hypotenuse, it requires a little bit less work. Okay? So let me see. Let me see something. I'm going to grab a different marker. Okay, that's cool. All right. So, and my recommendation to you, even though we did an example and we wrote the formula already, every time you do a problem like this, once you look at the problem, you know, take account of what you have, take an inventory of what you're looking at, and then you realize, okay, what formula do I need to use? Always do yourself a favor. Always write the formula down. Write the formula down every time. It don't matter if you're doing a homework assignment and you got to do 15 problems and you're using the same formula. Write the formula down 15 times. Do yourself a favor. It's not that much extra work, but it's going to pay dividends long run and in the long term because that helps you to retain that information. Because you never know when you're going to be in a situation where you need this formula on a standardized test, on an SAT, in the next math class. Just write the formula down, right? All right. So again, we have a right triangle because we have a right angle, and we know two legs and a hypotenuse. We don't know the hypotenuse. Hypotenuse is missing. So I'm going to use the Pythagorean Theorem, or a squared plus b squared equals c squared, to figure this out, right? And now I want to figure out what x is, right? So now I want to figure out what c is. Before we figured out what b is. It could have been b or a, but we figured out what b was. Now we're going to figure out what c is. And how do I know that? Because this is the hypotenuse. This is the hypotenuse. The hypotenuse is always across from the right angle. The hypotenuse is always across from the right angle. Memorize that. The hypotenuse is always across from the right angle. So now, for my legs, I got a leg that's 5 units, and I got a leg that's 13 units. All right? This is definitely out of scale, the way I drew this. But that's okay, though, right? Because this leg looks like it's almost as big as this leg, but yeah, this leg is 5 units, and this one is 13 units. I hope y'all noticed that. But no, it's not to scale. So when you're doing problems and you see shapes, and then it says figure not drawing to scale, that's what that means, right? All right, so let's replace our letters with numbers because we want to replace our letters with numbers just like we do when we use any formula. Any formula. So I'm gonna make my A5. I'm gonna just go counterclockwise. Make my A5 and my B13. I don't know what C is, but I'm gonna replace it with X. All right, and now I just, remember order of operations. Do not add 5 plus 13 and get 18 and then try to square those. Don't do that. Don't do that. That's not cool. All right. Follow the order of operations. Order of operations, PEMDAS. Even though sometimes you divide before you multiply, right? You got to use your exponents first before you do addition. You got to use your exponents before you do addition. Don't forget that. Respect the order of operations. Respect it. Respect the order of operations. All right? 5 squared is not 10 because we're not doing 5 times 2. We're doing 5 times 5. 5 times 5 is 25. And again, we got our perfect squares memorized, right? Perfect squares is memorized. 13 squared is not 13 times 2. It's 169. Boom. 25 plus 169 equals x squared. Add these two up. 169 plus 25. 160 plus 20 is 180. 5 and 9 is 14. 180 plus 14 is 194. So we got 194 equals x squared. Now, I'm thinking to myself, 194 I already know is not a perfect square because I know that 196 is a perfect square because 14 times 14 is 196. All right. I also know that 169 is a perfect square, right? Because 13 times 13 is 169. So there's no number in between 13 and 14, right? So 194 can't be a perfect square. Now, next question. Like in example 1, is there a factor of 194 that is a perfect square? I already checked. There isn't one. Besides 1, if you want to be technical, 1 is a factor of everything. But that's why 1 doesn't change anything. 1 can't help us. Because if you break this down into 1 times 194 and then take the square root of 1, you're still going to have the square root of 194. All right. So let's write it. Matter of fact, let me switch markers. So let's write it. We're going to have the square root of 194 is equal to the square root of x squared. So that's just x over here. And the square root of 194, we would just leave it. Right? If you want to have your answer in radical form, right? In radical form, you will leave it as 194. But if your teacher wants you to write it in decimal form or not in radical form, and round it to like 2 decimal places like we did here with 8.49, then we would have 13.93. That would be our answer for number 2. All right. So this is how we use the so-called Pythagorean theorem in certain situations when we're missing a leg. This is how we use it. In other situations when we're missing a hypotenuse, this is how we use it. And again, don't forget, the hypotenuse is across from the right angle. It's across from it. All right? All right, well, please like the video, subscribe to the channel if you haven't already. Tell somebody about these videos and share them. You know, tell a lot of people. All right? And as always, remember that there's all this math all around you. Peace.